Quantum entanglement, a concept even Einstein didn't understand, is now in your physics textbook, and you don't understand any of it. Well, thanks to John Bell, this once challenging concept can be explained in much simpler terms. So you may be wondering why you have to learn about quantum entanglement and why it will be important in your life. And while it may not be really important to your job description later on in life, it really helps physicists and scientists now make the bridge between the quantum world and the classical world. And what the quantum world is it's the world that describes such small stuff that you can't see it with the human eye or even some of the most powerful microscopes in the world. It's stuff like photons, which are particles of light, and millions of photons bounce off you every minute. I mean, more than millions. They're so small they just pack up everything. And so they're trying to use stuff like quantum entanglement to link this to the classical world, which is stuff like this leaf, or like the bowling ball you used the other day, or I mean anything to the pencil or your textbook. And so they're trying to build stuff that's such a minuscule thing to the large things we see in everyday life. So the particle that Einstein and John Bell used to represent quantum entanglement is what's called a photon. And a photon is a single beam of light that's a wavelength, and it has multiple wavelengths, such as it can be gamma, ultraviolet, and ultraviolet, which color of ultraviolet, X-rays, etc. And so what they did is they took this single photon and they sent it through a special kind of crystal. And the crystal split it into two separate photons, creating them at the exact same time. And what this does is it quantumly entangles the two photons. So you'll have photon 1 and photon 2, and they will always be entangled in their spins, which is their angular momentum, or the momentum of the photon when it's going in circles, like spinning or circling or orbiting, etc. So what this does, if we measure the photon spin of photon 1 at an angle of 0 degrees, and it gives an upspin, due to quantum entanglement, we now absolutely know that when we measure photon 2 at the exact same 0 degree angle, it will have to get a downspin, and vice versa. And this is because quantum entanglement shows that when they're measured at the same degrees, the two will have to have opposite spins, because as the law of conservation of angular momentum states, when two photons or particles are at the same degrees and measured at the same time, they have to counteract, so it would be positive, negative, it would give like an equal charge in an ion bond. So what this does is, whenever they're measured at the same angle, one will always be up and the other will always be down, and the spins will always have to be opposite. And so this doesn't matter no matter where in the world they're measured. They could be measured at the same exact place, they could be measured light years apart, they could be measured from a distance from the Earth to the Moon. The distance can be infinitely far apart. However, the quantum entanglement will always result when measured at the same angle. They will have the opposite spins. So now let's take this quantum example of the photon spins and relate it to something classical that we can wrap our minds around. And we're going to use Oreos. And so what this will represent is we're going to have the vanilla side represent photon number 1 and the chocolate side represent photon number 2. And the angle at which they come in contact with the cream will be the angle at which the photon spins are measured. And whenever we have the rough side out, it's going to be considered an upspin, and the smooth side out, as is shown here, we're going to have as it considers a downspin. So now this cookie follows the rules of quantum entanglement, as you have the same angle and it will equal the different types of spins. So now let's create some more examples. If we have something like this, where it comes normally, we have an upspin on photon 2 and an upspin on photon 1, and they're both interacting with the cream at the same angle. So this will not be allowed by quantum entanglement, as well as the law of conservation of angular momentum. Another example that could be made is when we have where they're both perpendicular. We have one here and the other here. So this would not be allowed, as they both are now facing the same way when they interact with the cream. Whereas if we flip this side of the cookie, it's allowed, and that's destroyed, as a photon would be if it's captured by any sort of lens or your eyes. So using this example, we can always remember quantum entanglement using Milk's favorite cookie.